Again, we will continue our set of dynamic programming classical examples, and we reach the fifth problem type, which is the coin change. We are revisiting this problem since we saw it already in the greedy paradigms, but we said that the greedy solution is only good for some of the denomination sets and not all. And here we go, we recall the problem. Given a target amount V cents and a list of denominations for n coins, so we have the coin value of I for I is between 0 and n minus 1. We are asked for what is the minimum number of coins to use in order to represent V. So we can represent V supposingly, and we are interested in the minimum number to use in order to represent V. And for this first version, we will assume that there is unlimited supply. So you can use as many coins as you want from each type. It depends on the coin system, in fact, if for you to decide if greedy or dynamic programming solution will give you first the right answer. If greedy will give you a right answer, you can use it. It depends on the coin system. If the coin system is canonical, you can go ahead and use greedy. But if the coin system is arbitrary, you cannot use greedy. What is canonical? Canonical, most of the coin systems in reality are canonical. You don't have, if you want to return a change, you don't have many possibilities. You can use if you take the maximum and if you subtract always subtract the maximum, the greedy will be a fine solution. So let's take an example in order to understand what's happening. Suppose we only have a coin system of 2 coins, so n equal 2, and the coins values are 1 and 5. And we want to represent the target amount V, which is 10. So, in order to have a 10, knowing that there is an unlimited supply, you can either take 10 pieces of the coin value 1. This gives you the amount 10, and the number of coins is 10 also. Or you can take 2 pieces each of value 5, and this will give you the number 2 of coins. Or you can take 1 piece of value 5 and 5 pieces of value 1, which has the number of coins 6. And the optimal solution, because we are asking for the minimum, is of course 2. Let's take the example 2 and examine it. Here we have 4 types of coins and the target value is 7. To represent 7, we can either take 2 coins of value 1 plus 1 coin of value 5, which gives me a total number of coins equal to 3, or the only other possibility is I can take 1 coin of value 3 and 1 coin of value 4, which gives me the optimal number of coins 2. And here we can clearly remark that the greedy solution would not have worked because if we proceeded by taking the maximum first, we will end using 3 coins. That's why we are studying this version, the general version, in the dynamic programming part. This and to find the states and the recurrence and the recurrent relationship between the states. The state here is the value, which is the remaining amount to represent. And when the value is 0, so we counted all the pieces and there is no remaining amount, so we return 0. When the value to be represented is a negative value, and since we are searching for the minimum, in order to state that this is impossible, we will return a high value so that the algorithm will cease considering this case. This is also a base case, but a negative base case, let's say. And the general case is the minimum in order to represent a value is uh, is for a certain state, for a certain value, is the minimum of 1 plus the change of value minus the coin value I, and this is for each I. So if you try for each coin value, uh, what is the minimum to represent for each coin value? We subtract this coin value from our current value, and what is the minimum of coins to represent it? Plus 1, because the coin value at consideration. So the minimum amount will be returned by our function. We will see this in a while. We will see a detailed example, and we will say now what is the number of cases, what is the number of states. The number of states is the number of values, of possible values. So uh, this is V, and what is the complexity of each to calculate each state, since there is for every y in 0 to n, so we multiply by the complexity n. So the overall complexity is O V times n, and we start by calling the change of the target amount V. So this is the function, the recursive function. Every time you have the value v to represent, it's either one of the base cases, you return the appropriate return value, and then we use memoization in order to not do overlapping problems, to not recalculate overlapping problems, because obviously there is overlapping problems here. So what we do, we local reference the memo of value, and if in case it is not calculated yet, we calculate it, or we return the answer if it is already calculated. So how do we calculate it? We search for the minimum. We search for the minimum. Uh, we initialize answer at a high value because we are searching for the minimum, and from I equals 0 to n minus 1, we see which value of 1 plus change of value minus coin value is the minimum, and we return this answer. Let's take the example 1 and see what happens when I try to execute this function. So first I have our memo table, one state, so the memo table is one-dimensional, and it has an additional zero index based case, and the items are going from representing the value amount 10 to representing the value amount 1 or even 0. Okay, so let's go. Suppose the target value is 10 and I want to know what is the minimum coins I can use to represent this target value. Knowing that the coins I have are of type 1 cent and 5 cent. In order to calculate it, I have to know, is it having the minimum number of coins to represent 5 cents plus 5, because I have a coin of value 5. So is it adding a 5 value to the minimal number to represent the value 5, or is it adding the coin of 1 to the minimal number to represent 10 minus 1, which is 9? So this is the answer here. We begin by calling the state 10. 10, in order to represent it, it is equal to 1 plus the minimum between the change of 10 minus 1 and the change of 10 minus 5, because one time we subtract 1 and one time we subtract 5. In order to calculate 10, this is a top-down approach, as you can see. we need to calculate the change of 9 and change of 5. To calculate the change of 9, we need to calculate the change of 8 and change of 4. Since they are all initialized to -1, we have to go down 8, 7, 6, 5, 4, 3, 2, and at last we reach the change of 1. Change of 1, in order to calculate it, you have to calculate the change of 0 and the change of -5 and to decide which is the minimum. Change of -5, we already explained, it will return a high value. So change of 0, it will return 0, so the minimum is 0. And we get state of 1 equal 1 plus 0, and this is it. We will put 1 here. We will go, we were using the state of 1 in order to calculate the change of 2. So based on 1, change of 2 uses change of 1 plus change of -3, which is a base case. And now I can have change of 2 because it is 1 plus the change of 1. Similarly, change of 3, change of 4, and then I have the change of 5. Change of 5, what does it tell me? If you have change of 4, which is 4, and you have change of 0, it is a base case, it is 0, then the minimum between them is of course 0, plus 1 is the change of 5, so I return it and I memorize it at the same time. And this is how change of 6 and memo of 6 will become 2, and then of 7 will become 3, because from 5 and up we are going now 1 unit further, bigger, and then change of 8, and I reach change of 9, which is 5. In order to calculate state of 10, I need to know what is the minimum between change of 9 and change of 5. But you have deduced now that since we are using memoization and we need the value of change of 5, we already memoized it and we have it in the order of 1 now. So it will be equal between the minimum of 1 and 5 plus 1. Okay, so either we use the coin 5 and plus 1 we add another coin of type 5, either we use the value for obtaining 9 and we add one coin of type 1, and of course the value for 10 will be equal to. And you can notice this is a top down, we went down and then we went up, but going up didn't cost us lots of operation, but it cost us the winding and the unwinding, however. So it's better to do this using a bottom-up approach. So let's consider the bottom-up approach. As you can deduce from the top-down approach, you can deduce that always when you have to calculate a state, you will be obliged to calculate the previous state. So why not beginning by calculating the states from 0 and up? So this is the bottom-up approach. We will initialize mem set to a maximal value and mem 0 to the base case 0, and then going from I equal 1 to the value, the maximal value that can be asked for, we can do memo of I is equal to a big value, but we will not initialize it to int underscore max, because here we are going to add a value, to add a 1, so for not to overflow, this is one of the solutions, we can put it here. So int max -1, and we do the loop, and inside the loop every time I can subtract the coin value of j for j equal 0 to n. If I minus j is greater than 0, then a memo of I is the minimum between memo of I and 1 plus memo of I minus cj. Okay? And else it will remain the same. So if I can subtract the value of a certain coin, I subtract it directly, and I add only one because this coin is only one piece. And this way I fill the bottom-up approach, and let's see a demo. So let's see the demo. The first we will see the top-down approach. Here is our function change, and here is our function main, in which we initialize the memoization table to -1 values, to dummy values. -1 is very fine since we are searching for the minimum. A minimum number of coins cannot be negative. And we begin. This is a static coin system. This is only for trying. So we have a non-canonical file system, coin system, which is the example 2, I think. And then we have our change function, which takes the value, and that we have already explained. Let's run this code for the following target values. For the target value 7, I have 2, the 2 is the minimum. For the target value 1, I can represent it using one coin only since I have the coin 5. For the target value 10, I can use 2 coins, and 11, I can use 3 coins. Let's see now the bottom-up approach. So we will see now the bottom-up approach. So here, and here is our input data, and I will delete our output data. And here is our bottom-up approach. As you can see, for each value amount, I can go, and for each coin value, I can iterate, and then if this amount, if this value amount can hold the coin value, current coin value, if the subtraction is positive or 0, then the memoization is the minimum between the current memoization and the one added to the memo of I minus Cj, and I run, and I will have exactly the same result. So this is logically faster in this case, and this is a demo of coin change problem. Is not only other than calculating the minimum number of coins to be used, is the different calculating the number of ways we can in which we can represent a coin change. So this is a UVA 647 entitled coin change, and here we have 5 types of coins. This is canonical, by the way, and we want to represent it. So this variant of the problem, of the coin change problem, you have to count the different canonical ways to get the value v cents using a list of denominations of n coins. And we have still the condition of unlimited supply. So since we said 2 times canonical coin system, canonical weights, let's recall what is the meaning of canonical. This is string Madame Curie, and this is another string radium came. And if you can see, if we choose to represent the letters in the string in the ascending alphabetical order, we will reach the same canonical form. So if we agree all that the canonical form of a string will be the sorted form, so you will always get one representation for this problem. So in mathematics and computer science, a canonical, or we can say a normal or a standard form of a mathematical object, is a standard way of representing that object as a mathematical expression. Often it is one of which provides the simplest representation of an object and which allows it to be identified. So here in this problem we are asked the number of canonical ways. So for example, the 5 and 1 to represent the value 6 is the same as 1 and 5 because canonically this is the same solution, so we don't count it twice. So here our complete search recurrence relation will, in addition to the value that we used in our previous state, we will add the other parameter for the state, which is the type. And why we add the type? Because we want to know at each iteration which is the index of the current coin we are studying, for not to count a double counting, for not to double count a state. And this is because we want the number of canonical ways. So we go from 1, 2, 3 to 5, or from 5, 4, 3 to 1, but not in arbitrary direction. And in this way we are double counting the cases. So here also the complexity is order of n times v, and for each state the complexity is 1. Why? Because this is the code. Here, instead of taking the minimum, I take all the possible ways, but there is no a for loop, because I don't check for in each state for every other coin. I check for the next coin type only. So the answer is it will return an integer, which is the number of ways, and the state is the type and the value. And now let's examine the base cases. If the value equals 0, I return 1 because I don't have a remaining value to represent. I represented them all, so I reached a solution, and this is counted one solution. If the value to be represented is negative, this means the money is negative. This is a negative base case, so I will return 0. So this is not a solution and should not be counted. If the type is n, since I'm going from type 0 till type n minus 1, if I reach the type n and the value is not negative, because look here, the value, is not null, because the value null is in the case just before. So if I still have money to be represented and I tried to take all the possible coins and I didn't arrive, so this is not a solution. I return 0. And in the general case, I local reference answer to memo type value, which is initialized to 1. This is also the top-down approach again. And the answer is the number of ways to represent the type plus 1. So to represent suppose I skip this coin type. Suppose, for example, I am now at the coin type 25, and I decided to use none of the 25 coins, so I skip it. So what is the remaining value to be represented for the next type? It is the value itself, the same value. So this is the number of ways. I count them and I add to them the number of ways that I can have if I decided to take one piece of this value. So if I decided to take one piece of this value, the remaining value to be represented will be value minus coin value of this type. But the next state type will remain the same type, because I have an unlimited supply, so I can decide next maybe I take another 25. So this is an order of one operation for each state. And how many states do I have? I have the interval where type varies and times the interval where value varies. So n times v times 1. And this is our problem. And here let us see this interesting thing. Since in the UVA 674 in the given, let's recall the given, you are given a fixed coin type, So for our interest, when we fill the memo table for the next target value in order to calculate it, we don't have to reset the memo table because it will be always valid, so it can be used. And this will reduce dramatically the time complexity. So let's see a demo. Here is our code. The exact same code I have showed you, and these are some of 74 test cases, and let's run it and see. Okay, it will write on the out file, and this is it. In order to represent 0 coins, I have only one weight, and this is the base case that was given in the problem description. In order to represent the target value 57, I have 62 possible ways, and so on. This was the top-down approach, and let's see the bottom-up approach. Also, the bottom-up is very similar to the previous one we saw. And here, instead of taking the minimum, we are taking the sum. So first, for I equal 1 to the number of coins, for s equal 1 to the maximal target value that can be given. So this is a two-dimensional memo table, and memo of is first at initialization memo of I minus 1 s, and if we remove the value of the coin I minus 1 from s, it will still be a positive value. Then I will add the case in which the ways. So I will add the number of ways possible when I remove it. So the number of memo of I s minus c of I minus 1, which is the value of the coin. Okay, and this is the value of the sum, and it is surely calculated because this is a bottom-up approach, so it was calculated before calculating memo of is. And this is the solution. And lastly, of course, the optimal solution, the final number of ways is inside the last, and is inside the last table, just like we saw in the knapsack example. So let's see a demo. Here is our exact same code with the same test cases we saw with the top-down approach, and we can run it in order to verify the output. So here is our bottom-up approach. Back to the slides, let's recall something, let's note something that in the bottom-up approach, also in this case of problem, we only fill the memo table once before reading the different target values. We fill the memo table, and now we can deal also in order of one with all the requests. So this is interesting. Another interesting thing to notice here is that in this line, note with me the memo of I, how it is calculated at each iteration. For each I, memo of I depends only on the memo of I minus 1 and on the previous row. So this is the only thing we need. So just recall the space optimization we used in the previous classical examples. We can use it here. We only need in fact, not of the previous row, of the previous of the previous row. So we only need a one-dimensional memo since we are calculating from left to right. So we use the old value and we replace it, and the next column will use the updated value. So we remove every two-dimensional state, we remove I and I minus 1, and we keep only the state of value, and this gives us a memo 1D and the updated formula. I put only once before the double loop, memo of 0 equal 1, the base case, and then I double loop, and at each time I update memo of s. I don't need anymore this line, memo of I s equal memo of I minus 1 s. It is already equal to itself, and then I update it only if the I update it if the condition applies to the memo of s minus c of I minus 1. Okay, let's see a demo. This is the code we just saw. Let's erase the output and reproduce it again. So this is a third running for the same problem solution, this time with a bottom-up and space optimization. Variant of the coin change problem is the following. Suppose we remove the unlimited supply available and we have a problem with a limited supply. What shall we do? Only one, suppose you are given a problem, only one piece of each coin type, okay? If additional condition, I repeat, a coin cannot be used several times. It can either be used, either ignore, either take, but you cannot take, for example, 2 coins of 5 cents. How do we modify our solution from previously? We cannot cumulate anymore. So what shall we do? For the inner loop, we calculate it based on the previous states, but before update and not after update. So in order not to take into account the update, and since we are using the space optimization, we are using only one-dimensional array, what shall we do? We go from the end to the beginning of the array, and each time I update based on the old value. This way I don't give myself the chance to take into account 2 pieces of the same type. And let us see here, let us remark here that for the static example given in the code, this is a canonical coin system, and here we can understand more why it is called a canonical coin system, because inside a canonical coin system it is the number of ways to represent a value, knowing that you can have only one piece of each coin type is always either 0 or 1. There are no different ways to represent a value. Let us see a demo, and this is our final demo for this problem example. And here we have the reverse inner loop. And let's take an example on this set of data. To represent 6, we can have one possible, you can imagine only one possible method to take a canonical way, canonical method. So this is a canonical coin system, and they want us to count the canonical ways. The canonical ways is to take 1, 5, because taking 5, 1 is the same canonical way. So to take 10, is it possible to represent 10 knowing that we have only we can use only one coin from each type? Of course not. So let's run this problem, this code, sorry, and I'll allow you to write. And here we have, oh, of course not, I said, because I thought we have 1 and 5 only. We have the coin 10 type, so I have one way to represent 10, one way to represent 15, to take 10 plus 5, one way to represent 16, I can take 10 plus 5 plus 1, but I have 0 ways to represent 200, because in this case I have to repeat something. And in order to represent the value 13, for example, I cannot, because I have to take 10 plus 3 times 1, and this is not possible in this variant of the problem. So here we end our coin change problem. We saw different variants of this problem, and we tested them all.